In the previous lessons, we have learned how an electrolytic cell works and what happens when you pass a current into different kinds of electrolytes. So in this lesson, we're going to learn a new kind of cell. So previously, we have learned that electrolytic cell actually uses a current to break down a compound. Alright? Now we have learned previously in the topic of energy changes that the breaking down of a compound actually requires energy, and the term for that is called endothermic. Alright, so what an electrolytic cell does is to convert a current or electrical energy into the chemical energy required for the breaking down of a compound. Now we have also learned in chemistry that there are certain reactions that gives out energy, and we call them exothermic reactions. So with a suitable kind of cell, with the suitable setup, we can actually convert this chemical energy into electrical energy, with which we can use to power our appliances. Alright, cells like this are called galvanic cells. Now for the chemistry behind galvanic cells, we'll only learn it in A levels. In O levels, we'll learn two specific kind of galvanic cells. One of them is called a simple cell. The other one is called a fuel cell. Alright. So now let's take a look at the components of a simple cell. It looks like an electrolytic cell, and same thing, there are three important components. The first component is your electrode. Alright, second one is your electrolyte. So these two are the same as for your electrolytic cell. However, for a simple cell, if you recall, this time we do not need a current to start the reaction, but rather a current is being produced by the reaction. So the last thing that we need is for something to measure the amount of current or the voltage that is produced in the cell. So in this case, we are using a voltmeter. Okay, so the first difference between a simple cell and an electrolytic cell is that a simple cell uses a voltmeter, an electrolytic cell uses a battery. That's the first difference. Okay, there's a second difference, and the second difference is this: in an electrolytic cell, usually both electrodes are made of the same metal, alright, or same substance, which is graphite. But in a simple cell, the two electrodes have different metals. Okay, so for example, one of them can be zinc, the other one can be copper. Alright, so now with this particular setup, let's look at what can happen when you have this combination of electrodes. Now if we look at zinc and copper, the first thing that we need to assess is this: which is the more reactive metal? If you can recall your reactivity series, zinc is actually your more reactive metal. Okay, because it's above copper in the reactivity series. Now what does it mean when we say that a metal is more reactive? Is that the metal has a greater tendency to lose electrons. So when you connect zinc to copper, what is going to happen is that zinc has a greater tendency to lose electrons, so zinc will give away its electrons to copper. Alright, and when zinc loses electrons, it actually becomes oxidized to form zinc ions and electrons. Alright, so this is what's going to happen at the electrode on the on the left, sorry. So as the same rules apply for simple cells, is that the electrode where oxidation occurs is called the anode. Alright. Now after the electrons reach the electrode on the right, now what is going to happen is this: can copper take in the electron? Answer is no, because copper is also electron rich. It doesn't want to take in the electron. So what can take in the electron? Now we need to look at the ions in the electrode. So the electrode in this case, or in most simple cells, are aqueous acids. So if we look at, for example, sulfuric acid as the electrolyte, the ions present in your electrolyte will be H plus and SO4 2 minus. Alright, so of these two ions, which one can potentially be reduced or can take in the extra electrons at your copper electrode? It would be your hydrogen ions. Okay, so at the cathode, what is going to happen is that your hydrogen ions are going to be reduced, are going to take in the electrons and are going to be reduced to hydrogen gas. Okay, so I'll do a quick summary. What happens when you combine zinc and copper electrodes together in a simple cell is this: is that zinc, being the more reactive metal, has a higher tendency to lose electrons. So as a result, it will be oxidized to form zinc ions, and it will undergo oxidation at the anode. The electrons are going to flow to the other electrode, which is your cathode, and at the cathode, hydrogen ions are going to take the electrons and they are going to be reduced to hydrogen gas. So like the case for electrolytic cells, we have to be able to predict what are some observations. The first observation is this: if zinc anode is being oxidized to form zinc ions, you will find that your zinc anode actually becomes smaller. Alright, or it dissolves into solution. At the cathode, what you will observe is that you will observe bubbles or effervescence forming. Alright, this is due to the production of hydrogen gas at the cathode. Alright, and then of course the last observation that you will see is this: because a current now flows through the external circuit, you will see a reading on your voltmeter. For example, something volts. Now one last thing to take note is this: as mentioned, the anode, which is made of zinc, is the electrode that has a greater tendency to lose electrons. Now electrons are negatively charged, so in this case the anode, because it has a higher tendency to lose electrons, it carries a negative charge. Whereas compared to zinc, copper is the electrode, or is the metal that has a lesser tendency to lose electrons, meaning a greater tendency to take in electrons. So the cathode has a positive charge. So what we see here are the half equations of the reactions that are happening at the anode and the cathode. So to recap, at the anode, your zinc anode is going to be oxidized to form zinc ions, and at the cathode, your hydrogen ions are going to take the electrons and become reduced to hydrogen gas. Now let's try to combine the two half equations, and if you can recall, in order to combine them, the first step is to ensure that the number of electrons on the left side of the equation is equal to the number of electrons on the right. In this particular example, the number of electrons are the same, so we can proceed to combine the two equations together. And when we combine them, we actually have the following ionic equation. Now, by staring at this ionic equation, I don't know whether you all can realize that this actually represents a reaction that we have learned before. Alright, this reaction is the reaction of a reactive metal with an acid. Alright, so if you don't believe me, you can write out the chemical equation for zinc with any acids, and then when you reduce it to the ionic equation, you will actually arrive at this particular equation that I've written. Now, the reaction of reactive metals with acids, if you can recall again from the topic of energy changes, this reaction is actually exothermic. What it means is that the energy will be released in the reaction. Now, if we simply allow the two reactants to mix, what will happen is that the energy will be released in the form of heat. But what happens when we set up a simple cell is that we force the electron transfer to occur in an external circuit. So we force the electron to flow through an external circuit, and that will generate a current. So effectively, we are converting the chemical energy into electrical energy. Okay, as mentioned, there are three outcomes. The first of which is that the zinc electrode becomes smaller, or it dissolves into solution. At the copper cathode, the hydrogen gas is formed, so you see bubbles, and lastly, you will see that there's a reading on your voltmeter. Okay, before we go on to the next example, I just want to remind you again that the anode, being made of zinc, which is the more reactive metal, is the negative electrode this time for a simple cell, and then at the copper electrode, where is the less reactive metal, it is the positive electrode. Alright, so essentially, electron flow is still the same. It flows from your anode to your cathode. Alright, or you can see it in this way. In a simple cell, electron flows from the more reactive metal to the less reactive metal. Now we're going to look at another example now. In this example, instead of zinc, previously we were looking at zinc and copper. Zinc at the anode, copper at the cathode. Now what happens if I were to change the anode into magnesium? Alright, so will I get a larger reading on my voltmeter, or will I get a smaller reading on my voltmeter? Alright, for those of you who can recall the reactivity series correctly, you will recognize that magnesium is an even more reactive metal than zinc. Alright, that means that the magnesium has an even stronger tendency to lose electrons. So what is going to happen is that obviously your reading is going to be higher. Alright, so because magnesium has a greater tendency to lose electrons, so there's a even larger electrochemical potential. Now, so essentially, what are we trying to learn from this example is this, that the voltage, alright, the voltage in a simple cell can actually tell us the difference in reactivities of the two metals in the electrodes. Alright, so if the difference in reactivity is large, you will end up with a larger voltage. Alright, and vice versa. So if the difference in reactivities are small, then you will end up with a smaller voltage. So as learned, let's look at this particular example over here. Alright, so if we look at the 5 combinations of electrodes, I have four unknown metals. The unknown metals are M1, M2, M3 and M4. All 4 metals are being paired with copper. Alright, and the following voltages are registered. Now before we go into analyzing the reactivities of M1, M2, M3 and M4, let's look at the 5th example first. When you have 2 copper electrodes in a simple cell, alright, both electrodes have the same reactivity, they have the same tendency to lose electrons. So what is going to happen is that the voltage generated will be 0. Alright, so if we look at the 4 examples above, you find that you have voltages produced for all 4 of them, with the voltage being the highest for the first one, where M1 is paired with copper. Alright, so what can we deduce from that is that M1 is the most reactive amongst the 4 metals. Alright, and then if we look at M4 registered the smallest voltage with copper. That tells you that it is the least reactive. Alright, so the reactivities of M1, M2, M3, M4 will be as shown. We have M4 being the least reactive, followed by M3, followed by M2, and the most reactive is M1. So before we go on to look at a fuel cell, which is slightly more complicated, I want to point out the differences between, or actually the difference, there's only one difference between a simple cell and an electrolytic cell. Alright, before we go on to the difference, I want to point out the similarities first. For all electrolytic cells and simple cells, the following statements that I'm going to say are the same for both. Alright, so regardless of whether you look at an electrolytic cell or a simple cell, oxidation always occurs at the anode. Alright, reduction always occurs at the cathode. Now specific for your simple cell, your anode is usually is always the more reactive metal. Your cathode is the less reactive metal. Alright, next, regardless of whether you're looking at an electrolytic cell or a simple cell, electrons always flow from the anode to the cathode. Alright, this is true for both cells. Specific to the simple cell, your anode is the more reactive metal again, and then your cathode is the less reactive metal. Right? So when you compare a simple cell and an electrolytic cell, there's only one difference, and the difference is this. In a simple cell, your anode is negatively charged and your cathode is positively charged. Alright, whereas for an electrolytic cell, your anode is positively charged and your cathode is negatively charged. Alright, so that is the only difference between a simple cell and an electrolytic cell. Now we're going to look at a hydrogen-oxygen fuel cell. Now for those of you who are looking at the textbook or referring to some textbook slides, you will notice that this example is not in the topic, it's not in the chapter of electrolysis, but rather it falls in the chapter of energy changes, alright, under the last part on fuels. Alright, so why are we talking about hydrogen fuel cell now? Is because hydrogen fuel cell is an example of a galvanic cell. Alright, so again, as mentioned, a galvanic cell is one that converts chemical energy into electrical energy. So how does a hydrogen oxygen fuel cell look like? It looks like this. So same thing, you have two electrodes. And then you have your electrolyte. Okay, your electrolyte is usually a strong alkali. For example, sodium hydroxide or even potassium hydroxide. Alright, so this is your electrode, and then your voltmeter. Okay, so in a hydrogen oxygen fuel cell, what's going to happen is that we're going to flow hydrogen in at the anode. Alright, and then we're going to flow oxygen in at the cathode. Now what is going to happen is this: at the anode, hydrogen is going to be oxidized to form water. Alright, at the cathode, oxygen is going to be reduced to form hydroxide ions. Alright, and essentially the product of the two reactions over here, later you will see, is that you will produce water. Now as mentioned, at the anode, hydrogen gas is going to be oxidized to water, whereas at the cathode, oxygen gas is going to be reduced to hydroxide. Now some of you may be wondering about this. Why is it that at the anode, hydrogen gas is not oxidized to hydrogen ions? And then at the cathode, why is oxygen gas not reduced to water but hydroxide? Now all this is because of the electrolyte. Okay, the electrolyte, as mentioned, it is usually a strong alkali, for example potassium hydroxide. Now under alkaline conditions, the redox reactions or the products that are formed will be slightly different. So again, we're going to learn this only in A levels. For O levels, what we require of you is to memorize these two equations over here. However, if you look at the cathode reaction, the equation looks slightly familiar because it is just the opposite of the reaction of the equation where hydroxide is being discharged at the anode. Alright, if you can recall, when hydroxide is being discharged at the anode, the half equation is actually the opposite one. Alright, so if you just need to remember, for hydrogen oxygen fuel cell at the cathode, when oxygen is being reduced to hydroxide, the half equation is the reverse of the half equation that I've told you all to memorize in the previous lessons. Alright, and then now if we try to combine the two half equations, we can see that the two half equations have the same number of electrons on the right and on the left. Alright, if you try to combine them, you will end up with the following overall equation. Okay, so there's also some meaning to this overall equation. What it's trying to tell you is that in an hydrogen oxygen fuel cell, we react oxygen with hydrogen to form water. Now why is this reaction so special? Previously we have seen the electrolysis of water, where water is being split into hydrogen and oxygen. Alright, and this takes place in an electrolytic cell. So what this tells you is that the splitting of water into hydrogen and oxygen is actually an endothermic reaction. So it requires energy to take place. Now, if the breaking up of water into hydrogen and oxygen is endothermic, when water is formed from oxygen and hydrogen, it tells you that this reaction is actually exothermic. Alright, so once again, if we allow hydrogen and oxygen to come into contact under the right conditions, this energy release will be released in the form of heat. However, if we separate oxygen and hydrogen, we don't allow them to meet, right? But rather we connect them using a hydrogen oxygen fuel cell. We actually force the electron transfer to take place in an external circuit, right? So the hydrogen will transfer its electrons to oxygen through the external circuit, and the result of this is that it produces an electrical current. Alright, so what this equation shows is the basis of galvanic cells, or simple cells or fuel cells, is that we use a reaction that releases energy. However, we don't allow the reactants to physically meet, but we force the electron transfer to occur in an external circuit, and by doing so we can convert the chemical energy into electrical energy. Now, a few more things to take note for a hydrogen oxygen fuel cell is that unlike a normal fuel, right, unlike normal fuel, where the energy energy release will stop when the reactants are used up, in a hydrogen oxygen fuel cell, the reactants are being flowed continuously. Alright, so as long as you continue to flow in oxygen and hydrogen, the fuel cell will continue to produce energy. Alright, the next thing is this, that the product of this fuel cell is water. Alright, as compared to maybe petrol, which produces carbon dioxide, the fact that it produces water tells you that the hydrogen oxygen fuel cell is environmentally friendly. Right, because the use of the fuel cell, or the use of hydrogen as a fuel, do not produce harmful gases. Alright, but do bear in mind one point, that water is also a greenhouse gas. Okay, so the presence of water vapor in the air can actually trap the infrared radiation, leading to greenhouse effect.